Last week saw the end of our paper 1 stuff, learning outcomes 1 and 2. This week we're starting learning outcomes 3 and 4, which we'll look at in detail in a minute. But on the first couple of pages of your notes I've given you out this week, there's some drill questions I'd like you to spend 5 minutes, 5-10 minutes having a go at before we actually start. So there's stuff about that function and graph on the first page, and there's some stuff about indices and roots on the second page. So have a go at those drill questions, see where we already are with this topic. Okay. Drill. So, what have we got for the term used for points I and B? What term will you use for those two? Oh, sorry. Peak and trough, okay. What might be a more mathematical term for that? Peak and a trough. I is the maximum. Okay. More completely, I the local maximum. B local minimum. Right? I can see why you might say peak and trough. They aren't really mathematical engineering terms. I'll give a point each for maximum, minimum, or peak and trough. If you've included the word local, you can have an extra point. The importance of the word local is you don't know, if you've just got a graph, you don't know what that function does outside the range you can see. So depending on, I mean, I know that there are no more maximum or minima actually in that function because I know the function I've graphed. For other functions, that might just be a small part of it, and there might be other maximum and minima in other places. Okay, so right, what's the value of the slope at points A and B? Slope of the graph, points A and B. Anyone got anything for that? The value of it, a number. No. We're going through the drill. So what would you say is the slope? What do we mean when we say the slope? How can I put the slope at a point on that graph? What would I be doing? Yeah. 0, yes. If I put the slope there, the slope has to be tangent to the curve. The only way it can be tangent to the curve is if it's horizontal, and that means the slope that hasn't got any slope, it's horizontal. The answer to that one, 0, both cases. Slope at A and slope at B is equal to 0. Point each if you got those. Indicate on the graph a point where the slope is positive and another where the slope is negative. Where on that graph might I be able to indicate a slope that's positive? In the first bit going up, so we could have a positive slope anywhere along that portion there. If I drew a tangent to it, I'd have a positive slope. Equally, I could go up there after B, and I'd have a positive slope anywhere up that line. Okay? So a point, if you have marked any position between B and the top there, or any position between A and the bottom, that would be where you'd have a positive slope. Consequently, you have a negative slope downwards on any point between the points A and B marked on the diagram. Point for that. Indicate the point that represents the root of this function. What do you mean by root? What do we mean when we say we're going to find the root of a function? We've covered this. Remember what it is? Go on. Parallel with 6. What, over here somewhere? No, that's not right, but any other ideas? It's here. That's the root. The value of x when y is equal to 0. We solve quadratic equations, we use that formula to find the roots. If you got that, you have a point for that. So on that page, I give 3, 2, 2, 1. So maximum at the moment is 5, 6, 7, 8. Value of x to the power of 1. Got an answer. Any number raised to the power of 1 equals itself. Answer to x to the power of 0. The answer is 1. Point for each of them. Any number raised to the power of 0 is equal to 1. Square root of 9. 1 point. There's another point to be had there. Plus or minus 3. So you can get 2 points if you've got plus or minus 3. Square roots, 2 answers, positive or negative. Plus 3 times plus 3 is equal to 9. Minus 3 times minus 3 is also equal to 9. Yep. Square root of 27. Cubed root of 27, sorry. 3 only, 1 point. Plus and minus, lose half a point. Okay, plus. Right, how do we write this in non-fraction form? No, that's still the same form. I want to move x cubed to the top, what happens to it? 3's got to stay. I want to bring x cubed up to the top line. What happens? Not remembering much from the earlier lessons, are we? The answer is 3x to the minus 3. We need to be able to do this. To do this calculus, we're now going to start. Okay? If we, just let me try and explain using the fact that we can write x to the o to mean 1. We could write that fraction as 3 times x to the o, and it's still the same thing, remember, okay, because x to the o is 1, so it's still the constant 3 over x cubed. And then remember the rule that when we divide indices, the answer is x to the o minus 3. Yeah? So that's 3x to the o minus 3, 3x to the minus 3. Those two things are exactly the same. Yeah? So if you move that x to the power from the bottom to the top, you change the sign. And you're going to need to be comfortable with doing that, really, without thinking too much. So if you did do that, you're going to have a point. How do we write those in indices for? First one, x square root of x. X to the power half, point. And 3 at the cubed root of x squared. No, not quite. Oh, hang on, yes it is, sorry. 2 over 3. Yeah. That one is the square, the number on the outside is the denominator, yeah. Sorry though. Point for that, alright? So that's another 1, 2, 3, 4, 5, 6, 7, 8 points. So the maximum you get is 16. Who got 16? Anyway, moving on. Learning outcome 3 and 4, calculus. Learning outcome 3, investigate and model engineering situations using the rules of differential calculus. Learning outcome 4, investigate and model engineering problems using the rules of integral calculus. So, 2 different halves to calculus. As you'll find out, once we've done both of them, they're mathematical opposites of each other. If we differentiate a function and then integrate it, we end up back where we started. It's a bit like multiplying and dividing, adding and subtracting, and so on. Okay? So assessed by 2R exam paper, paper 2, and there's a branch of mathematics involving or leading to calculations dealing with continuously varying functions. Falls into 2 parts: differential calculus, or for short differentiation, and integral calculus, or for short integration. If you have already done a BTEC, you'll have touched on it. If you only done Unit 4, you'll have done a bit more of an extensive look at calculus if you did Unit 28 as well. And if you've done A-level, you'll have definitely touched on calculus. Am I right, Tom? You did A-level, didn't you? But you'd have gone into a lot more detail on how it works rather than using it. We're going to use it, all right? So, functional notation we're going to take a look at first. In an equation such as y is equal to 3x squared plus 2x minus 5, so we're looking at a quadratic equation. It's got the highest power of x is 2. Y is said to be function of x to be written as y is equal to f brackets x. An equation written in that form, f brackets x 3x squared minus 3x minus 5, plus 2x minus 5, sorry, is termed a functional notation. What we can do is say the value of that function fx when x is equal to 0 is denoted by f bracket 0. value of that function when x is 2, denoted by f brackets 2. Then we can calculate or evaluate that function at different values of x to suit our needs. Okay, so there's two ways of writing it. You can write it as an equation as y is equal to something, or some other variable is equal to in terms of another variable, or you can write it in functional notation, and it depends on what you're trying to do, which one's the easiest to use. So, a little bit about the gradient or slope. We've already talked about slope a little bit, okay? If a tangent is drawn at point P on a curve, the gradient of this tangent is said to be the gradient of the curve at that point. So a tangent is at right angles to the radius of that curve at the point of interest. That's what a tangent is. In the diagram there, the gradient or slope of the curve is equal to the gradient of the tangent at PQ. No, tangent P to Q. Okay? Now, you can calculate the gradient at any point by looking at the gradient being equal to the change in y, written lowercase delta y, divided by the change in x, that's a lowercase delta x. You ain't quite got that far yet. It becomes dy by dx in a little while. Okay? At the moment, we can take any size of change to that slope and find the gradient at that particular point. If we can measure off any change there, any change there, so we can choose any point on that graph, measure those changes, and get the slope. Yeah? Right? So the slope is change in y over change in x. Yeah? So the rate of change, y with x, slope is. Next page. Later you will see that the gradient of a tangent to the curve f brackets x, if that function is x squared, is equal to 2. So effectively, the gradient of x squared is equal to if we consider the curve of f of x is equal to x squared as shown below, and we're only showing part of it, the gradient of the chord AB, so we're looking at this line at the moment, yeah, we've got a change in x of 2, and we've got a change in, oh no, hang on, what we've got to do is find what the function is at 3, that's there. We've got to find what the function is at 1. So we've got the value of the function at 3, the value of the function at 1. Okay, the value of this function at 3 squared is 9, 1 squared is 1. So our slope, if we take that chord, is 4. If we take it down a little bit further, what we're interested in is the gradient at point A. So if we take it down a little further to point C, our top line becomes a function at 2. 2 squared is 4. Take away 1 squared. We end up with a gradient equal to 3. The gradient of the chord AD, so we bring it closer still, 1.5. Okay. 2.25 divided by 1. 2.25. I got that wrong and all, didn't I? What's 1.5 squared? Not having a good morning this morning. It is 2.25. So that should, yeah, oh, hang on. That's 1.25 over 1 be 1.25. I.e., as the point B moves closer to point A, yeah, delta x effectively is getting smaller. We get closer and closer to the real slope. The slope of these chords, as we get successively shorter in the chord, is getting closer and closer to the actual slope at that point. Okay? Yeah. What is 1.5 squared? So that's that over 2.5 is right. You're noticing the mistakes, so that's a good thing. Okay. That's what, yeah, I do them all on purpose. Kind of what happens when you're under pressure to try and get right. We put it all right. It won't stop you being able to do the calculus that you need to do. Trying to get you to understand where it comes from briefly, instead of like Dom probably spent weeks trying to see where the calculus come from in A level. So, the differential coefficient, differential of a function. When this value of delta x tends towards 0, so as we make that change in x smaller and smaller and smaller, our chord is getting, as you've seen, is getting closer and closer and closer to the actual slope of that function. We can use two different notations for the differential coefficient. Once delta x tends to 0, we end up with what's called the differential coefficient. For y as a function of x, we can write the differential coefficient like this, dy by dx, as you said, Jay. Yeah? So that's how we would say that, we would pronounce that dy by dx. It's the rate of change of y with x. When using functional notation, the f brackets x, we can write the differential coefficient as f dash x. Yep. That means the first differential of the function f of x. So those two things, dy by dx, the same function, those two things mean the same thing essentially, the first differential. Okay. We're only going to be looking at first differentials this week. We'll just touch on successive differentiation next week. All right. Next week is more about the engineering uses of calculus, once we've learned the majority of the skills. So, what we're going to do is not worry too much about differentiation from first principles. Plenty of mathematicians over the ages have done all that for us to the level we need. We're going to be using a table of standard derivatives. Okay, so these are the ones you need to know how to use. There will be, because this is not a formula sheet, this is a table, right? There will be a table like that in your examination paper. Okay? So it's a table for you to refer to. So it gives you, for a range of functions, what the first differential is. Okay, and we're going to go through these anyway. But if the function is ax to the n, then the differential is a times n x to the n minus 1. If the function is e to the ax, then the differential is a times e to the ax. Log of a times x, natural log of a times x is 1 over x. Sine of ax is a cos ax, and cos ax is minus a sine x. They're the ones we're going to use. You will have that table in the exam. So let's have a look at a couple of examples. I. We've got y is equal to 12x cubed. Okay. The process is the index here, write that out again, the index comes down there and multiplies, okay, and then we take 1 off the index. So let's write that out. It is 3 times 12x is 3 minus 1. 3 12s are 36 x squared. We just pop back to the table. Have we followed the rule? If it's a x to the n, we bring n down and multiply, we take 1 off the index. Everybody happy with that? Yeah? Or not? Right. B. What we got? 12 over x cubed. What do you think we need to do with that one before we can... What do we do with the drill? Another way of writing that would be 12 times 1 over x cubed. Yeah, now what can we do to it? From the drill. Need to get rid of the fraction before we can differentiate this. So what do we need to do? Oh, not the table of derivatives, not 1 over x. So we need to bring this in the x to the power 3 up to the top. So we need to write that as 12x to the minus 3. Yeah. Then we can bring the dy by dx is equal to, bring the indices down, minus, I'm just going to write it out, bring the indices down and multiply, put the index, minus 3, minus 1. Yep, all happy with that? Then multiply it out. So it's minus 36, as you said, Lewis. X to the power minus 4. Okay. And if we wanted to take it back to our original form with the index underneath, how do we write that? no x on top. We can bring that back down into its original form if we want to. Either of those are the correct answer to that question. Okay? So if you had one like that in the exam and you give me that answer, haven't gone through that working, you'll get full marks. Okay? I'm not necessarily expecting you to take it back to that. You can do if you want to. Depending on what you're doing with this function, there might be a need to go back to that. That's the issue. Okay? So they're the first two examples using the rule in the first line of the table, which is if we've got a function that is constant times x to a power, we bring the power down and multiply, take 1 off the index. What about these two then? Y equals 6. How am I going to do that one? It's not in the table. How can we make it like something in the table? What's the power one? No, not quite. We need to have we need to have an independent variable in there, Dom, somewhere, don't we? So how can we put x in there and still have the right-hand side equal to 6? Look back to your drill. How can I 6? We could have it over x0. 6 times x to the power 0. You've got it. So we can rewrite that as y is equal to 6x to the o. Just want to I'm trying to show you here where the derivative of a constant comes from. Right? We'll see in a minute. So now apply the ax to the n rule to that, step by step, like we've done with the last answer. Tell me what the derivative of the constant 6 is. Did you get? Yep, correct. Apply that. The indices come down and multiply. That becomes x to the minus 1. Yeah? But nothing times anything is what? Nothing. When we differentiate a constant, the constant disappears. Think about a graph here of this function. There's our axes. There's the value 6. We graph the function y equals 6. It's a flat line. It has no slope. There is no gradient. So if we differentiate a constant in our function, constant disappears. Okay, so that doesn't matter whether that's 6, 10, 365, 10,286. The differential of it is nothing. It disappears. Okay? What about the next one then? Y equals 6x. What would be the indices applied to x there? It's implied. 6x to the power of 1. Therefore, if we differentiate that, dy by dx, we bring the 1 down, multiply, put the 6 in, x to the 1 minus 1, that equals 6. x to the naught, which is 6. So x terms, or terms with no index, differential as a constant, i.e. we're talking about a function that's linear. So again, it doesn't matter if it's 10x minus 3x 256x. Just drop the x off and you end up with a constant for that part of the differentiation. Are we all happy so far? Right. Now we got to rewrite that one so we can differentiate it. X to the 1 over 3. Now you can do it, can't you? What about the other one? B. We've got 5 over the cube root x to the 4. How can we rewrite that? Correct. Now you can differentiate it using the rules. So, a couple of minutes, finish off differentiation of those two functions. Right. Top one. dy by dx is equal to, what happens here? Bring a half down. Multiply by the 3x. So us half minus 1 is half minus 1. So that results in minus a half. So a half times 3 is 1.5 x minus a half. Okay. Again, you could write that as 1.5 over square root of x. Yeah. Right. Take that underneath. That would make it a positive root. But I'd accept that answer in the exam as a correct answer. I'd also take 3 over 2x to the power of half as well. You could leave that 1.5 as a fraction without any problem at all. Right, and in some cases, doing the use of differentiation, you're probably better to leave it as a fraction rather than turn it into a decimal. Right? So what about this one then? Yeah, we've done that there. So we got 5x to the minus 4 over 3. So we got to do minus 4 over 3 times 5 x minus 4 over 3 minus 4. So that's 6 minus 6 and a third then, I reckon. minus 20 over 3, x minus 7. Looks right to me. Right. We're taking away another 3/3 is what we're doing when we take away 1, aren't we? Yep. Okay. All right. Everyone happy with that? So, what we're going to look at now is differentiating a function that's got more than one term in it. So we've got y is equal to 5x to the 4 plus 4x minus 1 over 2 x squared plus 1 over root x minus 3. Okay? There's some bits on there we need to rewrite first. Yep. So we can leave that as 5x to the power 4. We can leave that as 4x. But we need to rewrite this bit. What do you reckon? You think that's 2x to the minus 2? Yep. Test it. Let x equal 3. Put that in your calculator with x equal to 3. Put that in your calculator with x equal to 3. See if they're the same. So 2 times 3 to the power of minus 2. 1 divided by 2 times 3 to the power of 2. Do you get the same answer? No, don't think so. Where caution is needed, right? Not the same answer, is it? So it can't be the same thing. It has to be the same thing. The way we can write that is a half the two's still got to stay on the bottom. There's only the x squared we're going to move to the top. You've got to do it like how could I write that and have an x on the top? So that's the same thing. I'd have to put x to the o there, wouldn't I? 1 times x to the o. So I've got 1 divided by 2 as a half, and then I've got x to the 0 minus 2. So the answer to that rewriting is that it's minus x to the minus 2 over 2. But probably a better way to write it is like this. Half x to the minus 2. So when we come to differentiate, we've got to multiply that by the constant in front of it. So that leaves it as a constant times that value. This bit, I've just thought of a better way to write that one out. This bit can be written as a half times 1 over x to 2. Is it not? When we multiply fractions, 1 times 1, 1, 2 times x squared, 2x squared. So we separated parts of that fraction. That's where our constant comes from, and the x coming up to the top makes the x a minus. Do you understand that now? Sense and not in some points of the room. Okay? But we have been through this, and you're going to get good at this. You're going to have to get familiar with it, at least for the duration of this course. Right? Okay. And then how can we rewrite this bit here? 1 over x, the square root of x. We want to bring it up to the top, get rid of the fraction. How can we rewrite x squared, square root of x? Minus. No x with that as a constant. Yeah. All we've done at the moment is rewrite those parts so that we got rid of fractions. Yeah. Now we will be, but what happens to 3 when we differentiate it? Constants disappear. Yeah. All we need to do to differentiate this function, find dy by dx, is differentiate each term one at a time. So when they're added or subtracted from each other, just differentiate each one. So here, we bring the 4 down, multiply, and take 1 off the index. So 4 times 5x cubed. That's x to the 1 here, so that becomes index down as 1, so that becomes just 4. Everybody happy with that? The x disappears. Minus 2 times minus a half. The index will become minus 3. Minus a half. X to minus 3 over 2. Minus 2 times a half we've got to do. Minus 2, I'll put down there because I'm differentiating it. Alright. Let that individual bit deal with the sign between the differential of that term and the differential of that term. Look at that as an individual part, including that sign. Yeah, that come from that, from there. Yeah? Okay. Then all we do is multiply out. So 4 5s are 20 x cubed. 2 times minus a half is, oh, hang on, we've got to go plus 4, we got that in there. 2 times minus a half is 1, so that must be plus x to the minus 3, 1 times x to the minus 3. Yeah, and then we got minus 3 over 2 times minus a half. plus plus 3 over 4 x minus 3 over 2. How to do this? This bit comes from there. That bit's on its own. That's from that term. Right. That comes from there. That bit comes from there. The constant on the end has gone away. When we differentiate a constant, it disappears. Try there to show where everything comes from. Why is not what half? You've got to multiply. Hang on. I have, yeah. It's already done. Right? Yes, bottom green line, final answer. Well, you didn't have it. You didn't have it in that form to start with, so you wouldn't do that. You might decide to make that 1 over x to the power 3. That bit. Yeah, you could do that. You could turn these into roots if you wanted to. Leave it is. That's 12 cos 4. Let's see if you can do the second one, B. Right, gents, B on the first of the 2 pages. We've got 2 cos 3t. What do I need to do? dy by dx is equal to keep the constant multiple of 2. Bring the 3 out. What's the entry in the table for cos of Ix? The entry in the table for cos of Ax. Minus a sine of Ax. So it's got to be minus 3, minus a is 3. In there a bit clearer than that. Minus 3 cos 3t. Yeah. Fine. Two times minus 3 is minus 6 sine 3t. Yep. over the page, y is equal to 3e 5x. What's the entry in the table for e to the ax? Sorry? A, e, the ax. Okay? Actually, that's why the e is a special number. Because e to the power of x, if we differentiate just e to the power of x, we end up with e to the power of x. Its differential is the function itself. That's why it's special. Yeah. Because if a is 1, we differentiate e to the x, we end up with e to the x. Yeah. So that's why it's special. So the answer to this one, what we got to do? Keep the 3, bring the 5 down, e to the 5x. 15 e to the 5x. V f theta equal to 2 over e to the 3 . What do I need to do with that one? Make it non-fractional. So I need to say that's equivalent to 2e to the minus 3. Now I can apply the rule. dy by dx is equal to 2 to 2. Minus 3 comes down. E to minus 3 theta. Minus 6 minus 2. Right. Then C was 6 ln 2x. Yeah, but f dash is 1 over x for ln x. That's the entry in the table. Yep. So you keep the 6, yeah, dy by dx equals that's the answer. Losing, isn't it? What it is. It's not what it's saying in the book. Honestly, I don't. We'll show you how to do that when you get the integration. Get your books out. Get your books out. What do the books say?